Thank you. So first I would like to thank the organizers. I'm happy to be back here in Lumini 20 years after. Yes, last time I came was 20 years after. Things have changed. Before, talks were in French. But now it's more international, which has also its merits. I would like also to thank my PhD students who have contributed to the research project supporting that presentation. So by alphabetic order, Xiaohui Chen, Hui Zhuanjing, Yushou Lei, Christopher Malijek, Xiantan Mukherjee, Dolanta Ashrafi, Lincha Wang, and Ning Xie. Also, I would like to thank my industrial collaborators, in particular Microsoft, industrial and academic, MIT CSL, NVIDIA, Intel, IBM of Canada, with funding support from Microsoft and IBM, as well as from MyTax and NSWAC of Canada, which are two funding agencies in Canada. And can you hear me well? Okay, good. With my cold, I don't hear myself well, but as long as you hear me, that's fine. Also, most of the algorithms and materials presented in this talk are part of the Maple's polyhedral sets library, which is in Maple now for about 10 years and which is evolving in almost every new edition of Maple, in particular for the coming one. I will start with some introductory examples, which actually gave me the opportunity to apologize. Here I had some LaTeX problems. You can see I think I've pushed LaTeX and Beamer to their limit because I have about 500 slides. And in some slides I have the word null, which has appeared here. I don't know why. I don't know if this is some comment from someone about my slides. But it's not on purpose. I don't mean that. I don't mean that something should be null. So what we see here is a system of linear inequalities in three variables, which form a representation of this polyhedral set. So here, this cubo-octahedron. And one important question in that area is that of computing the projection, or the different projections of this polyhedron. For instance, on the x1, x2 plane. So you can see here, so in that case, this is just that square, so that's relatively simple. But as we are doing, as we are computing that projection, many intermediate objects are computed, and these objects are most of the time not useful. In fact, they are redundant inequalities in the description of the projection. And they can be seen here. So you have these blue and orange lines. I will explain the colors later. And so an important part of this computation is to remove these redundant inequalities as early as possible. If you don't do that, then the algorithm is essentially doubly exponential in the dimension of the ambient space, whereas at the end, if you do that at the proper stage, then it's only singly exponential in the dimension of the ambient space. So projecting polyhedral set has many applications. So this is used in discrete optimization and also in the topic of optimizing compilers, which explain my connection with these different companies. I think here everyone would recognize a typical naive C code for multiplying two univariate polynomials. A natural question here is whether this can be parallelized, so if we can replace one of the for loops by a parallel for. Okay. In fact, this is not possible because of data dependencies, because different iterations here are accessing the same element in the output array C. So we have a write after write type of dependence. But this can be resolved if we reorganize the loop, more precisely if we do a change of coordinates. So there are techniques for computing this change of coordinates. So instead of talking about I and j, we can talk about two other coordinates. In fact, P for processor, meaning that one processor is in charge of one coefficient and t the time. And now we get another loop that we'll see in a moment, where parallelization is possible. Now, when we have discovered this change of coordinates, the question is for a compiler to generate the new code, in particular computing the loop bounds. So this can be done by this projection of polyhedral sets, which is to some sense a way of changing variable order. So here we write down all the constraints with the old variables I and j, the new variables t and p, as well as the input parameters n and m. And then we ask for reordering from this order where p and t is greater than I and j to this order where I and j is greater than t and p. So that's a way to get rid of I and j and just have t and p as functions of n and m. So that produces a new system of inequalities. You notice here that sometimes two inequalities are packed as one using min or max expressions. And from there, we can generate the multi-threaded code for our dense univariate polynomial multiplication. So compilers do these sort of things automatically using this projection of polyhedral sets. Now, this operation, which is also well known as the Fourier-Motzkin elimination, has many applications. I will show another one here, which is for computing the integer whole of a polyhedral set, which itself has application again in the area of optimizing compilers. So here we have a 3D pyramid, which is described by the system of inequalities. The vertices of that pyramid are some points which are not integer points, and the challenge is to compute the integer wholes, that is to describe all the integer points which are inside that pyramid. So later on today I will explain how it can be done. For the moment I'm just illustrating the algorithm. So there is a number of steps in the algorithm. There's a first stage called normalization, where we replace the input polyhedron with another one, a little bit inside with additional properties, so that the algorithm can take advantage of some properties. Again, I will explain that later. And after that, the algorithm decomposes this polyhedral set into regions. So there are essentially two types of region. There is a big red region in the middle, so the picture on the top left corner, which is essentially almost the entire thing. And that red region is also a polyhedral set whose vertices are integer points. Therefore, it is its own integer whole. So we are happy with that. It's maybe almost the whole thing that we want to compute. And then there are some thin regions around the red region where maybe we still have integer points that we need to take into account. So in these thin regions, which are blue, red, or purple, how do we search for integer points? Here we apply a brute force method. So we compute a sort of parametrization of these regions using Fourier-Motzkin elimination, or integer projection, as we saw earlier. Once we have this sort of parametrization, it is easy to search for possible integer points. Once we have the red integer points, which again are easy to find, it's essentially given for free, and the integer points of the other regions, we can put them all together, apply a convex Rel algorithm like quick-roll, and finally we obtain the desired answer. So the point I want to make here is that this Fourier-Motzkin elimination is used to handle these special cases, and this is why it's important to make it efficient. And at the end, our pyramid has an integer whole with, I think, 139 vertices, which shows that, yes, the problem of computing integer whole of polyhedral sets is not that easy. You can start with some very simple object and obtain something which is geometrically quite complicated. Okay. Now I'm returning to optimizing compilers. So here with, I would say, some very simple example. We have a two-loop nest in C. And as you can feel, the programmer aims at manipulating an object which is mathematically 2D, but is or she is using a 1D C array. And that's a challenge for compiler optimizations because due to this one-dimensional C array, the array references, that is the expression between the brackets, are nonlinear. And doing dependence analysis, that is, to be technical, essentially doing Presburger arithmetic with these nonlinear things, is difficult, right? So what we want to do here is to discover what can be, I would say, a 2D version of that loop. Here I'm just showing that, again, I have this null, I'm sorry about that. Trying to do dependence analysis here would bring these nonlinear expressions, and that would be potentially something that cannot be decided. So what we want to do with this for loop is to replace it by another for loop where now the array is truly two-dimensional. Okay, so here is the solution. But doing that is also something non-trivial. In fact, this problem, which is called the delinearization problem, is essentially a QE problem over the integers. And in its full generality, you have to deal with nonlinear things, so it's potentially non-decidable. But suppose you manage to do it, at least for some family of examples. Then after that, you are ready to start dependence analysis. So now the array references here with this new array B are linear expressions, so you can do your Presburger arithmetic. And so, for instance, on that example, the top system on the right is the one that you would like to consider on the original problem for deciding whether there are dependencies or not. But again, it's nonlinear, so not easy. But after doing the delinearization process, now you are left with a system of linear inequalities for which you can decide whether you have integer solutions. In this case, the answer is no, proving that there is no read after write or write after read type of dependencies in the second loop, and therefore it can be parallelized. So yeah, this problem of delinearization is very important in the compiler community because, again, if the original code is in C, and you have these one-dimensional C array that are used to manipulate objects that are in fact multidimensional, then you have these nonlinear array references. But in its full generality, this problem is difficult. So other things that we are trying is to do some sort of pattern matching. Let's say we can pre-compute some solution to the delinearization problem for certain problems, let's say 2D Jacobi. And after that, at compile time, check if some new code that we have is looking like one of our pre-computed examples. And so that's what we do. So how to detect if two things are essentially the same? So we want to find a linear transformation from let's say, a well-known pattern to a new code that we want to study. And this transformation obviously must be unimodular because you want to map integers to integers, because you want to map iterations of loop to iterations of loop, as well as rank preserving, that is, you want to preserve the order in which the different iterations are executed. And so this is what I'm explaining here. Here I'm giving definition of what I mean by rank preserving and why we want to be unimodular. I think okay, in this computer algebra community, everyone would understand why. And so these conditions, they can be phrased in a QE problem. So for instance, here for the case of 3D loops, so say we are looking for a transformation from a 3D loop to another 3D loop so that it is rank preserving. So here you have the QE input problem, the QE output, so that is what must be the properties of such a transformation. Of course, here I'm doing that over the rails because we have to deal with nonlinear things, so I cannot do that with Presburger arithmetic. And after that, I take into account the fact that I am dealing with integers, that I have a transformation which is unimodular, which after that limits the choice of the different transformation to a few ones. So this sort of computation can be done, I would say, offline. That is before we compile the program and try to decide if it's similar to something that we already know. At compile time, we have all these pre-computed patterns. And then we can start to see, okay, if this is matching this or that. At compile time, the array references of our programs, they are already known. That is the expressions between the square brackets. What we don't know at compile time is the value for the loop bounds, so typically n and m. But we can do some of these calculations at compile time. And then at runtime, when finally, let's say the loop bounds are known, n and m, so then everything becomes linear and the problem can be solved. Okay, so this was a little tour of the types of problems that we're interested here. So the topics that I will cover today and tomorrow the following ones. So first, there will be a sort of crash course about polyhedral geometry. That is, I'm not assuming that you are familiar with that. So myself, I studied pure math before doing my PhD, and I never heard about polyhedral set except for linear programming. So I may understand that you may not know certain questions in this field. So that's why I will start with a review of the key results. And after that, I will look at 4 problems. The first one was illustrated at the very beginning, that is solving a system of linear inequalities over the rational numbers. In other words, doing what is called Fourier-Motzkin elimination. And again, this operation is really core to many others. To some sense, it plays the roles of Grobner bases in this context. That is, many algorithms can be reduced to that. We saw an example earlier with the integer whole. So the next topic will be integer wholes. So I believe that this is where I will stop today. And then tomorrow there will be 2 other topics related to the integer points of polyhedral sets. The first one is counting the number of integer points, and in particular, doing that for parametric polyhedral sets. That is, when those polyhedral set depends on parameters, and still we want to be able to count the number of integer points, which means we are going to produce formulas about the number of the integer points. And a typical application of these things is, so again, given the for-loop nest, you want to count how many memory accesses, how many cache accesses are done by the loop nest. And the last problem would be quantifier elimination over the integers, that is, deciding Presburger formulas. Okay, so I will start with this review of polyhedral geometry. So my slides are quite dense. I try to write quite a few proofs, but I'm not going to go through all the proofs. They are there in case people are interested. And maybe I will use some of these proofs to highlight some key points about the proof, especially when the proof is constructive, which is the case, for instance, for the famous Farkas-Minsky-Weil theorem. For the following topics, so these are, in fact, sections based on talks given at diverse conferences, except for the last one, because that's recent work. So for the topics of Fourier-Motzkin elimination, integer holes, and counting integer points, I will refer to the articles for the proofs. But for the last part, quantifier elimination, so what we'll do tomorrow, we will go through all the proofs. Okay, so as I was saying, the first section is a review about polyhedral geometry. References that I'm following are the books of Alexander Shriver and Branko Grünborn. Notations are usual, in particular for the sets of integers, rational numbers, and real numbers. Most of the time, the dimension of the ambient space for me is D, except, okay, I have one set of slides where accidentally it became N. So most of the time we live in RD. There will be many symbols. There will be vectors, matrices. So I try to use uppercase letters for matrices and polyhedral sets, lowercase, bold letters for vectors and points. But sometimes, yes, and uppercase, sorry, lowercase, non-bold for scalars. And then I have some usual notation for the closure, the interior, and the frontier of subset of RD. Okay, so before talking about polyhedral sets, I will talk a little bit about convex sets, so giving some special examples, reviewing the definition of what is the span, the affine hole, the convex hole, and conical hole of some subset X of RD. So I think the span is something clear certainly for everyone, so all possible combinations of elements of X with real coefficients. Affine hole, so now we are asking for the sum of the coefficients to be equal to 1. If we talk about the convex hole, so now the coefficients must be non-negative and the sum of these coefficients must be equal to 1. And if we talk about the conical hole, that is the cone generated by X, so now the coefficients are non-negative, but their sum does not need to be equal to something particular. So some examples. So here I have an X which is in fact a few points. These few black points here. In red I have the convex hole generated by these points. And in blue the cone or conical hole generated by those points. To give a more interesting example, so the definitions are still the same over there. Now here I have a circle here in blue, and I'm interested in this conical hole, so it's easy to verify that this is in fact the half space, which is painted in light blue. So these objects have different properties, and one key tool to manipulate them is the Minkowski sum. You can view here. I believe this is also something that people are familiar with. So I have this Minkowski sum in blue of the two red and green polytopes. And a polytope is simply the convex hull of finitely many points. Okay. So as I've said, there are many properties that I'm listing here. This is for me to have a coherent and sort of complete set of slides of this topic. But I will skip quite a few because I think this is not the purpose here. So there are some basic properties about a fine hole and span, so something that people have certainly seen. Now there is something that maybe is less commonly known, so relation between the conical hole and the convex hole. So the conical hole of capital X is the set of the little x so that there exists a little t, so that t times x is in the convex hole. Or another possibility is simply that we have the origin. So to some sense, this is related to this Farkas-Minkowski-Weil theorem, sort of preparation to that. That is essentially how we turn a polyhedral set into a cone in one extra dimension. Again, I'm skipping the proof because I think it's not the goal. And I have a few more here. Okay, the next important notion is that of supporting hyperplane. So here I have a vector alpha in Rd and a scalar beta. And I'm defining the hyperplane corresponding to this vector and that scalar. And given some convex set, K, I'm saying that H supports K if one of the two formulas here holds. Later on, K will be a polyhedral set, and we will retrieve some well-known things. For instance, here, for my green polyhedral set, I have one supporting hyperplane, which defines an edge. It is the intersection of the supporting hyperplane and the polyhedral set forms what is called a face. Here I have a vertex, and here something which is not obviously a supporting hyperplane. So as I was saying before, a face is simply the intersection of a supporting hyperplane and a given convex set. Well, later on, it would simply be a polyhedral set. Most of the time, we're interested in faces that are proper, so that is, that are not the empty set or the whole set. So here we have some examples and counterexamples on the top left. In red, we have obviously a face of that little pyramid. In the middle top, we have one edge, again in red. Then clearly this is not a face because that's only a part of the previous face, and here the union of these two red edges itself is also not a face. I will skip that part because I think I will not talk about extreme points and exposed points, even though they are important in the proofs, but I will not need them. Okay. Okay, now something which is very important that we already saw a little bit is the concept of a cone. So in my space Rd, C is a cone if it is stable by multiplication by non-negative scalar. It's a convex cone if in addition it is stable by addition. And it is a polyhedral cone if in fact it is given by a system of homogeneous linear inequalities, as we can see. And it is finitely generated if, in fact, it is the conical hole of finitely many points. We have some examples of something which is a cone but not a polyhedral cone, whereas this one is a polyhedral cone, and we can clearly see, I would say, the rays which are generating this cone. Okay. Something that I think I can skip because I'm only using it in some proofs, which is the dual cone. Okay, so now we can finally define polyhedral sets. So we saw cone earlier, defined by homogeneous linear systems, and now polyhedral sets are defined by this system of linear inequality. So A is a matrix, X and B are vectors. So something which is the solution set of such a system of linear inequalities is what we call a polyhedron. And that system of linear inequalities is called the H representation of the polyhedron. As we will see in a moment, there is another type of representation. Because the polyhedron is then the intersections of finitely many half spaces, then it is clearly closed, topologically closed and convex. And here I have some examples of polyhedral sets, as you can generate them with the polyhedral sets package in Maple. Now, this system of inequalities, as we have seen at the very beginning, may contain some redundant inequalities, and we want to get rid of them. They may also contain what is called implicit equalities. So what are these things? So given one of the inequality of the system, so this C transpose X less or equal than beta, so one of the inequalities of the system AX less or equal than B, we say that it is redundant, essentially if we can remove it without changing the solution set. And we say that it is an implicit equality if, in fact, at any point of my system of linear inequalities actually satisfy the equality Ct x equal beta. So if I have an implicit inequality, so that typically means that my polyhedral set is not fully dimensional, which is what I try to suggest here. So I have something in the three-dimensional space, but it has an implicit equality. So in fact, it is only 2D. Okay, there's something I can skip. So different properties about these redundant inequalities. Yes?
I think I didn't catch the difference between implicit and redundant.
So a redundant inequality is an inequality that you can remove from the system without changing the system, without changing its solution set. Implicit equality, sorry, if I go back, means something like this. So it is given to you as as an inequality, but in fact, by combining with the other inequalities, you could deduce an equality. Okay. So that is, it may not appear clearly in the input system, but by combination, you may observe. Oh. Thank you for the question. So earlier I talked about the faces of a convex set. So now I'm focusing on the case of polyhedral sets. The definition of a face is still the same. So this is the intersection of your input polyhedral set and one supporting hyperplane. These faces are then themselves polyhedral sets. Then they have dimension in the sense of the Euclidean topology. The faces of maximum dimension are called the facets, and they play an important role that we will see in a moment. Those of minimum dimension are called the vertices. And there is one property which is often required by algorithm, is that your input polyhedral set is pointed. And so that means that this homogeneous system of equation has dimension 0. And so, for instance, if my input polyhedron is pointed, then my inclusion minimum faces are actually the vertices, that is the faces of dimension 0, which is, I would say, often the case in practice. Now, okay, so I will spend a little bit of time here because the faces are really important to understand, especially for the computation of integer wholes. So if my input system has no redundant inequalities, which again can be achieved by techniques that I will explain in a moment, then the inequalities of that system are in one-to-one correspondence with the facets, that is, those faces of maximum dimension. Yes?
Just a question on the linearity space. So your definition depends on the representation and not on the polytop?
Yeah, but in fact it's independent, yes. If you change.
For instance, an inequality, it's independent. Okay.
Thank you. So once I've removed all the redundant inequalities, then the remaining inequalities, the irredundant ones, are in one-to-one correspondence with the facets, that is, those faces of maximum dimension, which is a very nice property. Yes?
Don't you need to assume that we have a four-dimensional polyhedral?
For that, yes, maybe. Yes, maybe. Yeah, I was thinking about that last night, but then I couldn't find the reason why. I believe you're right. Yeah. So now, so more about the faces. So they can be ordered by inclusion. They form then a lattice in the sense of order theory. But this lattice is a bit special. It has a number of additional properties. First, it is graded. That is, it admits a rank function. I won't say much more about that. It is ranked. That is, maximal chains have the same cardinality. And there is this additional property here. If the ranks of two faces, where A is containing B, but the rank differ by 2, then there are exactly two faces lying between A and B. So that gives some special shape to the lattice. And the consequence of all these properties is the following. The face lattice of a polytope can be uniquely determined from its facet, its vertices, and the vertex facet incidences. So that is knowing for which vertex belongs to which facet. So if you know the facets, again, the vertices and these incidences, then you can deduce by pure combinatorial arguments the entire face lattice. That is, you don't have to do additional algebraic computations. It's only by, I would say, combinatoire des ensembles, so set combinatorics argument, that you can deduce your lattice. Okay, and so that property is important for algorithms. That means that, yes?
So when you say that you can order the faces, but you order the faces of the same dimension.
So they are incompatible. So this is a partially ordered set. So say, because it's a rank per set, so you will have, at the very top you have the entire space, then you have all the facets. I would say they are at the same level, they are incompatible. Below you have the facets which have one dimension less, and so on. Okay? And so there are algorithms which needs to explore all the faces of a polyhedral set, and so it's important to have this kind of result. So that means you only need to know facets and vertices to go through all the faces. Yes? No, polytop is a bounded polyhedral set. Polytop is a bounded polyhedral set. And by definition, this is the convex roles of finitely many points. Okay, oh, sorry, I should have skipped that, so I have some. So again, I have more things than what I can show clearly, so that's why I have this. Okay. Maybe I'm spending too much time on this basic concept, so again, I will skip more. There are two things that I want to highlight before going to the more technical parts, which are really central to polyhedral geometry. So first, what is called the Farkas-Minkowski-Vell theorem. So this is about cones. So I start with a convex cone, and the following two properties are equivalent. Either it is polyhedral, so that is, it is given by an homogeneous system of linear inequalities, or it is finitely generated, that is, it is the conical whole of finitely many points. So these two properties are equivalent. So here on the slides I have the detailed proof, and the reason I put that is because the proof is constructive. So that means that gives an algorithm for moving from one representation to another, that is moving from the polyhedral representation to the representation based on that conical whole. And it is something very important in practice. The algorithm which is in the proof is not the most efficient one, but it is essentially in the same complexity class as the practically efficient algorithm. So a practically efficient algorithm is the famous double description method by Koimi, Fukuda, and others. Okay, sorry. That algorithm is a little bit more technical than the proof, so that's why I have that proof here. So again, I'm skipping it. So once we have this, I would say, two possible description of a cone, we derive also two possible equivalent description of a polyhedral set. So this is what is suggested by this little picture here. So let's first focus on the little triangle here, so which is a polytop. We can embed it in a space of with one additional dimension. So we create a cone, okay, as suggested by this picture. And so there is a correspondence between that cone and that polytope, and more generally, we can make a correspondence between cones in dimension d+1 and polyhedral sets in dimension d. And thanks to that, we can, for a given polyhedron, move from its edge representation as we described it before, and a representation using what is called vertices and rays. So that is writing the polyhedral set as a Minkowski sum of what is denoted by Q over there, that is a polytope, and C, which is a cone. Okay, so again, I give the complete proof because that shows how things can be done in an algorithmic way. Yes?
Polyhedral and polyhedral set is
the same. Yes. Okay. And so if the polyhedron is given to you by an edge representation, that is a system of linear inequalities, you can get this Q and C, that is the vertices and the rays, using the vertex and rays command in Maple of the polyhedral sets package. Okay. And so yes, that theorem is really important. It is used to build other important results. But again, I will skip this. Okay, so now we know everything, or most things about polyhedral geometry. So I can start discussing the problem of solving system of linear inequalities, and more precisely, trying to remove those redundant inequalities. Okay, so I'm repeating my introductory example. So again, as input, I have a polyhedron in 3 dimensions, so this red thing here, which is described by its edge representation of this system of linear inequalities. And what I want to do is to project it in the x1, x2 plane. That is, I want to get this. In other words, this green region here. But as I'm doing this, I'm going to generate intermediate objects that are redundant. So actually, how do I generate this projection? Essentially by combining those inequalities. So essentially adapting Gaussian elimination to a system of linear inequalities, so which is the Fourier-Motzkin elimination process. So when I combine all these inequalities in all possible ways, again, I obtain many inequalities. Most of them are redundant. So this is this blue and orange line that we can see here. So there are only 4 things that are useful. All the rest is, to some sense, garbage. Okay. I'm not repeating my example of Fourier-Motzkin elimination applied to univariate polynomial multiplication. That slide repeats a few things that we have said, but not everything. This, no, this I've commented, that I can skip. That I can skip. That I can skip as well. So yes, just keeping in mind a notation. So again, typically we start with the edge representation of a polyhedral set, and then we want to compute its V representation, that is the vertices and the rays, that is the polytope and that cone as given by the decomposition theorem of polyhedral sets. In the subsequent slides, I will denote this pair of vertices and rays as the dual representation of my input edge representation. So this is just a notation. Okay, so finally an example of V representation. So considering this open cube, so given by this system of linear inequalities. So this cube has 4 vertices, so V1, V2, V3, and 1 ray, so that allows us to go to infinity above. So 1 ray, which is denoted by R over there. Oops, yeah. Okay, so how are we going to deal with these redundant inequalities? So let us fix an inequality L, so given here by A transpose times X less or equal than B. Let H index L be the hyperplane associated with that inequality. Yes, I will denote by K the number of elements in that V representation, that is the number of vertices plus the number of rays, because this is a sort of complexity measure of my input polyhedral. And I will so first review the definition of what is a redundant inequality. So that means I can remove it and still that describe the same polyhedral set. But I will need 2 finer notions. First, strongly redundant. So strongly redundant means that it's not only it's redundant, but A transpose times X is less than B at every point of my polyhedron. So that means that that line is really totally outside of the projection, as we could see in the image a few slides ago. Whereas weakly redundant means that at least for some point of the polyhedron, we have the equality A transpose times X equal B. So that means it touches a little bit our polyhedron. Okay, so our goal will be to discover these redundant inequalities. And the tool that we are going to use is an encoding of the relations between the vertices and rays and the different inequalities. And this encoding will be done through a matrix that we call the saturation matrix. So we say that a vertex V of our input polyhedron saturates a given inequality if simply that vertex lies on the corresponding hyperplane. That is, if A transpose V is equal to B. That's a very natural definition. And now for a ray, again for the cone part of our polyhedron, we say that it saturates the inequality if it is parallel to our hyperplane. That is, if A transpose times R is equal to 0. And then, so we build a matrix where we encode this saturation information. We are going to see, of course, an example of that matrix. So the columns of that matrix are indexed by the vertices and the rays. The rows are indexed by the facets or the inequality. And so for each vertex or ray, and for a given facet, so we put a 1 if that vertex or ray saturates L, and a 0 otherwise. So this is a Boolean matrix. So we have a little example here with a polytope. So on the top left, we have the edge representation with these 4 inequalities. In the middle, we have the V representation. So there are no rays because this is a polytope, so no cone part. And then we have the saturation matrix. So again, the columns are indexed by the vertices and the rows by the facets. And we have a 1 if that vertex is on that facet and a 0 otherwise. So it's a very natural notion. Okay, now with that tool, we will describe criteria to decide whether an inequality is redundant or not. So remember that dual F is our notation for the set of the vertices, comma, the set of the rays. If we write intersection with HL, we mean those vertices and rays that are saturating the hyperplane associated with L. And so for a given L, we construct the following matrix. So we take all the vertices and rays that are part of the saturation information associated with that hyperplane. We organize them in this way. So these are the columns of a matrix. And now we are ready to give a lemma about criteria for detecting whether L is redundant or not. We assume that the inequalities defining F are pairwise different. So I'm not saying that there is anything known about redundancy. I'm just saying they are pairwise different. Then the following conditions are equivalent. And I think this is kind of clear. So the inequality L is irredundant. So that's one property. It's equivalent to the fact that HL intersection with P is a facet of the polyhedron. And the affine rank of this, that is the rank of that matrix over there, is n minus 1. So this is a simple criterion, and this is well known. This is a sort of folklore to decide if L is redundant or not. Okay. So, but our goal is to take advantage of the saturation matrix as I've explained, because saturation matrix is a Boolean matrices, and this will allow us to do very sharp, I would say, implementation of this redundancy test. Okay. So we need a little bit more of notation, but these are the last ones here. So this notation SVRL collects all the vertices and rays saturating a given inequality L. So we saw examples of that before. There is a notation SHU. So now we collect the hyperplanes that are saturated by U, where U is either a vertex or a ray. We fix an inequality L, and then we compose these two sets, if I can say, in order to obtain the set of the inequalities saturated by the vertices and rays saturating L. Okay, now we come to the main theorem. That's essentially the last technical part. So the inequality L is strongly redundant if that SVR of L is empty, because saying that it is strongly redundant means it's totally outside, so that is, it does not saturate anything, so it's kind of obvious. If this SVR of L is not empty, but its cardinality is less than n, so that means some stuff is saturated, but not enough, then the inequality L is weakly redundant. But this is only an implication. And so there is a last part, which is now a necessary and sufficient condition for detecting whether something is weakly redundant. And this is where we use the composition of these two operators over there. So the inequality L is weakly redundant if and only if that set here is not empty. So that is, again, we collect all the inequalities that are saturated by what saturates L. Then we remove L itself, and then if that thing is not empty, then that proves that L is weakly redundant, and this is again a necessary and sufficient condition. So as we can feel, checking the first two is relatively cheap. Essentially, we look at the saturation matrix and we'll see it right away. For the third one, we need to do a little bit of computations to get there. I think I'm repeating myself here. Okay. Yeah, I think I'm repeating myself. Okay, so now, so thanks to this theorem that we saw before, we know how to detect redundancy essentially by looking at this saturation matrix. But this saturation matrix was built originally on the input polyhedron. So that is, again, its columns are indexed by the vertices and the rays of the input polyhedron. And then the rows are indexed by the, essentially, the facets or the inequalities. Once we have eliminated one variable, so in the process of Fourier-Motzkin elimination, so we are not talking about the same polyhedron, so we are in one dimension less, and so we need to update that saturation matrix in order to continue the process of detecting redundant inequalities. And so we need a way to update this matrix. And this is what we are going to see now. So here I'm just reviewing how we do Fourier-Motzkin elimination. So say that we want to eliminate a variable x. Y is denoting all the other variables. So here we consider two inequalities. In one, the coefficient of x is a1. In the other, the coefficient of x is a2. And one coefficient is negative, the other is positive. So that's an opportunity to combine them and eliminate x. Okay, that's the basic calculation in Fourier-Motzkin elimination. So this notation, proj of that pair of inequalities, is just the notation for the inequality that we build by Fourier-Motzkin elimination. So when we are eliminating x, we are going to combine all the inequalities. So every inequality where x has a negative coefficient with every inequality where x has a positive coefficient. So that gives us many inequalities. Again, most of them are redundant, and we will eliminate them thanks to the saturation matrix. But after doing that, we need to build a new saturation matrix in order to continue eliminating variables. And here there is, fortunately, a nice result. So we can compute the saturation information for the projected inequalities, that is the inequalities obtained by Fourier-Motzkin eliminations, by this formula, which essentially is a commutative diagram, so saying that the saturation information of the projection is the intersection of the saturation information of the input inequalities. So that means we can easily compute the saturation information for these new inequalities that the Fourier-Motzkin elimination process generates. Okay, so we have seen so how we use the saturation information to detect redundant inequalities, and we have seen how we can generate the saturation matrix for the next round of Fourier-Motzkin elimination. I've just kept the algorithms because I think these two key points are sufficient to understand the main idea, but again, okay, the algorithms are there. And so now we want to talk about the implementation. Because the fact that this saturation matrix is a Boolean matrix allows us to do some cool tricks, especially in a C implementation. That is, we can represent that matrix essentially with bit vectors. And the operations that we do on that matrix are essentially bitwise OR, bitwise AND. So that is the implementation of the theorem that I've shown earlier can be phrased into, yes, bitwise OR, bitwise AND on the rows and columns of that saturation matrix. So this is what I'm saying here. Essentially, there are two things that have to be done in that matrix. So first, detecting redundancies and then updating it. Because as we were saying, once we have done one round of Fourier-Motzkin elimination, we need to update the matrix to go for the next round. So these are essentially the two manipulations that have to be done. Some of these manipulations are on the rows, others are on the columns. And for that reason, we keep two versions of the saturation matrix or in the computations. Essentially, the saturation matrix and its transpose for cache efficiency reason. And because the saturation matrix can be large, we may want also to manipulate it by blocks of bit arrays. So I have to say that we have not done that yet in our C implementation, but I hope to do that in the next version. Okay. Okay, so now we'll talk about experimentation. So first, which criteria among the three that we have seen are used in practice to eliminate redundant inequalities? So you remember that there is that theorem. There are essentially two first points which are easy to check, and then there is one point which is a little bit more complicated. So the first 2 points corresponds to these blue and orange things here. So that is the detection of strongly redundant inequalities. So this is seen as easy. Then there is a criterion, but it's only a sufficient condition for detecting weakly redundant inequalities. That corresponds to these orange lines. And when these two are not sufficient to detect that something is redundant, we have to apply that more complicated point in the theorem where we have a necessary and sufficient condition that corresponds to green lines. But here on this simple example, there is no green line, meaning that we never had to use that more expensive test to detect redundant inequalities. In fact, I would say on simple examples in dimension 3, the first 2 points are sufficient to detect all redundant inequalities. Most of the time, as you can see, the blue one is sufficient. And in order to apply this third point, we had to create very large examples. So here we have examples in dimension 10, where we are eliminating, let's say, x9, then x8, and so on. And we can see that, yes, when we eliminate the first few variables, then that green and expensive criterion is applied. That is, it does most of the work. And after that, it's the cheaper criteria which are applied to eliminate the redundant inequalities.
Just
Yes?
wondering
I think I'm coming to this. Yes. So I have more examples to show that, yes, we need to build high-dimensional examples which have, where we need to apply that, I would say, expensive criteria. So now experimental comparison, and this will answer your question. So with other software, which are doing different things for eliminating redundant inequalities. So in this experimentation, okay, so we have first NPR, that's the name of the software that we use. Well, based on the algorithms that I've presented. Then there is a second implementation that we did a few years ago, also in C. So that was also so for eliminating redundant inequalities and using both the H and the V representation. But here, instead of using the saturation matrix, we use a technique called the redundancy test cone, inspired by Egon Ballas. But I won't say much more about that now. Okay, after that, so a well-known way of removing redundant inequalities when we manipulate the H representation is by using linear programming. So there is an easy way, so suppose that you have an exact method for linear programming, an easy way to check if redundant inequality, if an inequality is redundant by making a call to an LP routine. But our experimentation shows that in general, using things based essentially on linear algebra, so computing ranks and so on, is practically more effective than using LP. And also this is confirmed by complexity analysis. Another software that is used in experimentation is the famous Polylib, which can work with either the V representation only, so this is what you were mentioning, and or combining the H and the V representation. And the examples that we use, so we have random and non-random. Okay, so here this is comparing with this other software. So here we have, in general, in red, we have our implementation, so the algorithm based on the saturation matrix, so denoted by NPR. Then we have the CDD library of Koemi Fukuda and the Polylib library. So all these plots, this is in blue. So what are we looking at? So there are 4 families of polyhedral sets with increasing value for k. K is the number of rays plus the number of vertices, which is a measure of the complexity of the input polyhedron. And then we measure the time for eliminating 1 variable, 2 variable, and so on. So again, so our implementation is in red. So we see that as problems become more and more difficult, that is, as k increases, and this is performing relatively well comparing to the other approaches. And then we have timings for now well-known examples taken from the literature. We have the name of the example, their characteristic in terms of number of faces, number of variables, and the value of k, that is the total number of rays and vertices. the time for our implementation here, the time for our other implementation based on the redundancy test code, times for CDD, and time for polylib. And essentially, as problems become harder and harder, the NPR code is doing pretty well in comparison to the other ones. But there are some examples where the polylib is doing also quite well. Yes?
What's the time limit in the paper?
I forgot. It's in the paper. I think it's about. I think it's. I thought it was half an hour, but I see that you have this greater than 5 minutes, so maybe it's. Yeah. So these things are in seconds for sure.
So the unit is
In seconds, yes.
5 minutes.
Yes. Yeah. Okay, so now complexity analysis of so here I think, yes, the dimension of the ambient space is n and no longer my d like in the first slides, and m is the number of inequalities. So if the input system is irredundant, so that means the number of facets. And so, these two numbers are important to measure how things are hard, essentially to have estimates about the size of the V representation. So in the middle here we have this m to the n divided by n factorial, so giving an upper bound for the total number of rays plus vertices. Here there is another upper bound for the number of inequalities that we expect after eliminating the redundant ones, so essentially m to the n. So the algorithm that we have presented has two parts in the complexity estimate. There is one part where we compute the new inequalities. So this is done essentially by manipulating the coefficients. And in this case, we can give, we estimate bit operations because we want to take into account the growth of the coefficients. So this is this number here. Theta is the exponent of linear algebra. H is the height of the input system. And we also estimate the number of word operations that we do when we manipulate the saturation matrix, because again we have to do these bitwise operations on the columns and the rows. So that is a separate some account that we are doing. So how does it compare with other methods? So first, we may want to see how it compares with methods based on linear programming. So here we need to give a name to how much it costs to process a linear program. So say we are in dimension D, and H, what is H? Is the total size of our input problem. So then LP of D and H is this quantity. So you see D to the 3.5 times H squared times log H, etc. So this is in the case of Karmakar's algorithm. So we use that LP time for giving an estimate for the complexity of FME based on LP, so the first quantity in red. So that is an estimate that we gave some time ago. Then if we use the method based on the redundancy test cone, here is the estimate here. So here this is clear that techniques based on cones and linear algebra are more efficient than those based on linear programming. And in comparison to the saturation matrix, so things are not so clear. So the part where we just do the operations on the coefficients is better comparable to the estimate for the redundancy test cone, but there is that number here which is a little bit too high. This is where we do the operation of the saturation matrix. But in practice, things work well. So if we implement this type of algorithm, let's say in a high-level language, yes, maybe this won't have, I would say, significant improvement with respect to another method. But once it's implemented in C, because we can really take advantage of that saturation matrix, then we have the benefits of that method. Okay. Oops. Oh, I think I should almost stop there for today. So yeah, I'm not sure I can start the other part that I wanted to do, but integer whole. I think the remaining time is a little bit short, so maybe it's better for me to stop here and take questions.
Okay, so any questions? Yeah, thank you for your talk. Any questions? You already had so many questions, but I guess we have 5 more minutes. We can ask them.
Yes.
Thank you for the talk. I was just wondering, in one of your comparison of software, is there what is using a polymake in the table that you showed? And if yes, which column? Sorry, which column is it? And
Polylib, yes.
polymake, yes, polymake software, which I think is in Sage also. Or at least there is an interface.
I'm sorry, I did not understand.
Sorry?
Sorry, can you repeat?
Yeah, I was just wondering if one of these libraries is used in the polymake software. Or
Maybe I have to admit that I forgot. There are a number of libraries which are sharing common parts, so like the ISL, I think ISL and Polylib, they have common bodies of code, and I forgot if Polymake has also common parts with Polylib, but I don't remember.
What happens when the polyhedral code is the full dimension?
For the question of removing redundant inequalities? Yes, so yes, the method does not apply. Actually, yes, it requires that the input is full dimensional and pointed. So in the Maple implementation, when we are not in that case, then yeah, we use the redundancy test cone. So yes, that does not apply.
Thank you, Marc, for the presentation.
Thank you.
I have a question. In the examples that you consider the matrix A was dense, no? In the previous slide. Here, I mean, the matrix that you are considering, the matrix A is always dense, no?
Yes.
So what happens when the matrix is sparsity? Is it something that might, might that right for the kind of efficiency you consider?
That I don't know. Yeah, that's a good question, but that we have not investigated that. But most of these examples from the literature are sparse. All these true problems, I would say, problems coming from application, they are kind of sparse. Yeah. So in particular, this problem coming from scheduling, I mean, from optimizing compilers, they are typically sparse. Yeah. Yes. But we don't have a specific method to take advantage of sparsity, so that's next step.
Okay. Other questions? No, I think it's good to point out that Marc has kindly put like his slides on his homepage. Maybe you want to look at them like before the second lecture.
Yes.
Okay, super. Let's thank the speaker again.
Thank you.